Hello there. We will now talk about Chapter 12, Section 1, which deals with the chi-squared Section 1, which deals with the chi-squared test of goodness of fit. So chi-squared tests are just that. They're just tests. That'll be Sections 1 and 2. We got three different kinds of chi-squared tests. So there's no intervals in regards to chi-squared. It's just three tests. And so once again, whenever we do a test, we have to follow the same acronym: type of inference, hypotheses, assumptions, mechanics. Has some new looking stuff here, and then the ending. And so much of this is very similar to what we've had in the past, but there'll be, some different stuff. And the first thing, when do we use a chi-square test? And that is when we have a categorical variable that has two or more categories. Okay, it can't be quantitative. It can't, in other words, categorical in regards to people would be like, let's say, what state you're born in, or what race you are, or or in regards to, like, let's say something like trees, it could be, something like the type of tree, an oak tree, an elm tree, or something like that. But it's not quantitative. Okay, it's not like how high the tree is in feet, or it's not like with people how tall they are, how much they weigh, and something like that. It has to be a categorical variable. And we had categorical variables before when we did proportions, but it had to be a success failure situation. There could be just two options. In other words, it would be a proportion where we had, like, whether someone was a Republican or not a Republican, okay, or whether they were born in Alabama or they were not born in Alabama. Just two options. Well, now we can have two or more options. So with categorical, we can have, whether they're Republican, Democrat, Libertarian, or other, and what state were they were born in, Alabama, Mississippi, Georgia, Florida, or whatever. So now we can have a number of categories. Once again, it can't be quantitative. So that's one of the big questions. It can't be like, let's say, a test score, or, the amount of time they do something in seconds or something. So anyway, but with a chi-squared test goodness of fit, you're always going to have your null hypothesis is always going to be these proportions. So let's look at a couple of examples, and so hopefully this will be clear to you. So Manny runs a catering company. His company must provide food for the NASA employee carnival. They decide that each carnival attendee will get either an enchilada, nachos, or a burrito. Manny thinks that 20% will want an enchilada, 30% will want nachos, and 50% will want a burrito. For planning purposes, he decides to test this by taking an SRS, a simple random sample, of 80 of the employees. In the sample, 25 say they want an enchilada, 20 say they want nachos, and 35 say they want a burrito. Does the sample provide statistically significant evidence that the percentages above are wrong, and thus Manny needs to adapt his catering plans, perform an appropriate test? So provide statistically significant evidence. That means we got to find ourselves a p-value. All right, and you notice that this variable is a categorical variable with three categories. That means chi-squared. So that's an alliteration. Okay, that's an alliteration. Categorical, when you have categorical variables where the numbers are counts and categories, it's chi-squared. Okay, it's chi-squared. All right, and so our type of inference, and so I've written this out, and so you have to follow the same acronym. So the first thing, our type of inference, is what we call a chi-square goodness of fit test. So we've got, a few more. That's, so you have to memorize that. So anyway, so in general, with a chi-square goodness of fit is you're going to have these hypothesized proportions or percents that you're going to test against. So, and so the premise we have going on, we're expecting 20% enchiladas, 30% nachos, and 50% burritos. And is our sample that so different from those percentages that it would cause us to doubt it, to reject it? In other words, we got 25 out of 80 that wanted an enchilada, and 20 out of 80 that wanted a nachos, and 35 out of 80 that wanted a burrito. And that's different from those percents. But, and so is it statistically significant different? Well, that's what we're going to find. All right. So the null so here, then your hypotheses. Okay. So now your null hypothesis is in this section is always just going to be whatever the stated proportions are. And so make sure and define your proportions. And so P sub E is the proportion of all the carnival attendees that want an enchilada. So you're just going to state the proportions. That is going to be your null hypothesis. Your alternative in this section is always just going to be that at least one of the above proportions is wrong. That will always be your alternative. So So there you go. There's your null. There's your alternative. Now our assumptions, of course, I think you know our acronym for assumptions is SIN. And it's still going to sort of be SIN, but we're going to adapt it a bit. So our assumptions are our conditions. We have to make sure that we're getting good data. And we've adapted. It's actually a little bit easier with chi-squared. All right, the first two things are the same. All right, it has to be an SRS, and we've had this for like 6 chapters now, okay? It has to be an SRS or a simple random sample, so random conditions met. So that's what you would say. Nextly, for independence, our sample size has to be less than 10% of our population size so that our formulas will work, okay? And so so you take your sample size, which is 80, all right, multiply it by 10. And so we've had that for, there must be at least 810 E's for our little n to be less than or equal to 0.1 times our big N, because we're doing sampling without replacement here. Okay, and then lastly, all right, so in regards to normality, we do not have normality. No, we do not have normality in this section when you're doing chi-squared. Okay, so that's the little tweak. So don't mention the word normal in chi-squared in section 12.1 or 12.2. Your condition is going to be that all of your expected counts, which I'm going to show you how to find those, had to be greater than or equal to 5. So it's actually simpler. So for chi-squared, for the next 2 sections, these are going to be your conditions. And you make sure, and by the way, show your expected counts. And what that means is that our test statistic is going to follow a new distribution for us called a chi-squared distribution. And so here it is on table C on the back of your formula sheet. A chi-squared distribution is going to look something like this, and our test statistic is going to follow this, and we're going to find this area to find our probability or our p-value. But so don't say normality. We don't have normality in this chapter. All right, so how do you find the expected counts? Well, the expected counts are going to be the expected number in each category if the null was true. Now, our sample size is 80. So our N is equal to 80. So if we're expecting 20% enchiladas, our expected count for enchilada is just 0.2 times 80, which would be 16. The expected number of nachos is 0.3 times 80, which is 24. And the expected number of burritos would be 0.5 times 80, which is 40. So to find the expected counts, so I'll just write this out. To find the expected counts, multiply the null hypothesis proportions times the sample size. Okay, and you have to show those somewhere in the problem. All right, so let me show you what this little chart is. Well, here's the expected counts. So the expected count for enchilada is just 80 times 0.2. So it's that. The expected count for nachos is that, and the expected count for burritos is that. You have to make sure they're shown somewhere, okay, like that. So what does this table mean? Well, and I'm going to show you how to do this by hand. You can use the little shortcut with your calculator that I'm going to show you in a minute, but I think it's important that you understand how this is done by hand. So what we're doing is this when we're performing a test. We've made it to the bottom here in regards to our test statistic. A chi-squared statistic follows this formula. It's going to be the observed values, in other words, the sample values, minus the expected values, which we have found, squared divided by the expected, okay? And then, of course, that means add, and then we're going to add them all up. That sigma means add them all up. And so that is the formula we use to find our test statistic. And then once we find our test statistic, we can use that to find our p-value. So in order to find this formula here is the observed values of the sample value. So the sample value are just the numbers in your sample, okay? They have to be integers, okay? They have to be integers. The observed value. The expected values frequently are not, so don't round them to the nearest integer, by the way. So don't round the expected values. That's an important thing, actually. So there's my observed values. There's my expected values. And so to work with this formula, if we were doing this by hand, we would take observed minus expected. So I just say 25 minus 16 is 9, and I say 20 minus 24 is -4, 35 minus 40 is -5. Okay, and then the observed minus the expected squared over the expected. So then to get this, I just square that, it's 81, and divide by the expected value of 16. For this one, I square -4 and get 16 and divide by the expected of 24. With this one, I square -5 and get 25 and divide that by 40. I add these up, and that right there is my chi-square test statistic. And it is that is not an X. It is the Greek letter chi, and it is the capital Greek letter chi. And that is our test statistic. It is what we're going to use to find our p-value. And so once we've done that, so once we found our chi-squared test statistic, we can then use our calculator to find what our p-value is. Now, the premise going on here with this is that this chi-squared test statistic follows what is known as a chi-squared distribution, which is always going to be a right-skewed distribution. And the value to the right of it, with chi-squared, the p-value is always to the right of it. The area to the right of it is our p-value. Okay, now, chi-squared distributions, there's actually a large number of them, okay? And so similar to t-distributions, we have to define the degree of freedom in order to name which chi-squared distribution it is. The degrees of freedom is just the number of categories minus 1. So here we've got 3 categories. So it's the number of categories minus 1. So our degrees of freedom is 2. That tells us which chi-squared distribution we are working with, okay? And all chi-squared distributions, by the way, are right skewed. And the more, I guess, the fewer degrees of freedom, the less right skewed it is. Like if you had 1 degree of freedom, your chi-squared distribution would actually look like that. Okay. But if you had, something like, let's say 10 degrees of freedom, it's going to look a little more rounded and it's going to go like that, something like that. So, anyway, that's not that important for you to know because we're going to use our calculator function to find this. All right. So once we found this number, how do we get our p-value? We're going to use chi-squared Cdf. And so this is how we do that. So we're going to go to second distribution, just like normal CDF or t-CDF. And we're going to scroll down to chi-squared Cdf right there. Remember the CDF functions, they're p-value finders is what they are. So chi-squared Cdf. Your chi-squared value always goes on the lower. So in this case, it is 6.3541667. All right. And the upper value is infinity. So you can just put like 9 billion or something. The degrees of freedom is 2 in this case. And so there we go. And so so there's our p-value. Okay. And then after that, your p-value statement is just, now the p-value statement is not anything new. We've been doing it for several chapters. This p-value is less than our alpha. So I reject the null. There's convincing evidence that, and then you restate the alternative in context. There's convincing evidence that at least one of the caterer's proportions about carnival food is wrong. Make sure and mention the context. But so the p-value statement is exactly what we've had before. So, so this is in essence doing it by hand. Okay, now let me say this to you. Okay, now let me show you how you're really going to do the mechanics here, because you don't have to do this every time. So here's the little shortcut. This is what you're going to do to find your p-value and your test statistic. All right, we are going to go to a chi-square goodness of fit test. All right, well, I'm sorry. First thing we've got to do is we've got to enter our observed and our expected values in list 1 and list 2. So in list 1, so we're going to go stat, we are going to go edit, and in list 1, let me clear those out. So clear and down arrow, I'll clear those out. And in list 1, I put my observed counts. So the observed counts, that's just the sample values given in the problem, 25 and 20 and 35, okay? And then I put the expected counts in list 2. And let me just remind you how those are found. The expected counts, your sample size is 80. And so the expected is just going to be 80 times 0.2 is the first one, and 80 times 0.3 and 80 times 0.5. And so you could just say 80 times 0.2, that's 16, 80 times 0.3, that's 24, and 80 times 0.5, and that's 40. Now, once again, do not round your expected counts if they weren't integers. Your observed values have to be integers or you're going to get an error. Your expected counts can be decimals, and so don't round them to the nearest integer. That's sort of a common error. But then once you've done this, you're going to go to the chi-square goodness of fit test. So you go stat, you go tests, and you go down to the chi-square goodness of fit test, which is sort of down toward the bottom. There it is. So that's the chi-square GOF is the chi-square goodness of fit test. So that's for section 12.1. This next one, this chi-squared here, that's for a two-way table, which is in the next section 12.2. But this is the one we're doing in this section here. So we hit enter on that. And so my observed in list 1, my expected in list 2, my degrees of freedom is 2. And you hit calculate. And so there it is. So there is the chi-square test statistic, your p-value and degrees of freedom. So those are the only three things you had to write down. These three things are what I circled. So here's your p-value. Make sure and label it as p-value, by the way. But so that's all you have to write down is what I circled. And so there you go. And so that's how you do a chi-square test. Now, the next thing is what is known as a follow-up analysis. A follow-up analysis is just looking and seeing which category contributes the most. In other words, to the chi-squared. In other words, which one is most different? Okay, we're hypothesizing that these proportions, well, which one are the most different relatively? And that's what these numbers tell you. 81 over 16, 16 over 24, and 25 over 40. You'll notice it's the enchiladas that are the big difference. So in our sample values are not that different from our expected values relatively for nachos and burritos, but for enchiladas, they're sort of way different, okay? So in fact, and so when it does ask for a follow-up analysis, you want to look at these numbers, okay, these numbers, and this number is the biggest one. So when it asks, okay, follow-up analysis, in other words, which categories contribute the most, we would say the enchiladas contribute the most to the chi-squared with 81 over 16, which is 5.0625. You know, the whole chi-squared is 6.35. So this difference contributes almost all of it. Okay, now your calculator, by the way, because we've done this test, because we've done this goodness of fit test, see what these numbers are? That's what is known as contributing factors to the chi-squared. And there's our number. If you arrow over, you can see the other contributing factors. Or if you wanted to look at them, especially if you had a large number of them, you could copy them in a list. You can go stat and edit, and then just go to the top of list 3 like that, and then go to your list menu, go second list and scroll down, and it'll have your contributing parts to chi-squared. That CNTRB is the contributing parts to chi-squared, and that's created if you've done the chi-squared test. And you hit enter a couple times, and there it is. And so there's the contributing parts for chi-squared. So it's mostly the enchiladas that are contributing to that. Okay, so that is that. And that's how you do a chi-square goodness fit. Let me do another example, and this has one little curveball that could happen to you. So let's look at this example. So this one says a botanist wishes to test the belief that the colors of the flowers of a particular type of plant occur in the ratio 7:3 for red, yellow, and white respectively. He takes a simple random sample of 124 of the plants and finds that 70 of them have red flowers, 47 have yellow flowers, and 7 have white flowers. Does this data give the botanist reason to doubt the belief in the 7:3 ratio? Perform a test. So the tricky thing about this is they don't give you the percents like they did in the other problem. They give you this ratio thing. And you also need to perform a test. You'd say, well, okay, this is definitely a categorical variable. The color of the flowers is not quantitative. You know, these numbers are counts in categories. They are not quantitative numbers. Okay, and that means we're dealing with a chi-squared situation, and this would be a chi-squared goodness of fit. We call it a goodness of fit. Do the sample values, how good do they fit into this 7:3? Okay, and so we call this a chi-squared goodness of fit test. Once again, it's the same thing. Our null hypothesis is just the stated proportions. Okay, how did I get 7/11, 3/11, 1/11? That is just, in essence, this ratio of 7 to 3 to 1 for red, yellow, and white. So what you do to find 7 over 11, so you'd say, well, for the red, it has 7, there's a total of 11 parts here. And 7 of them are red. So for the red, it's 7 out of 11. And for the yellow, it's 3 out of 11. And then for the white, it's 1 out of 11. So that's how you get these proportions out of this ratio here. Just add them all up, and that goes on the bottom. And then each category gets the number that's in it like that. And so your null is just the hypothesized proportions. And then the alternative, once again, is going to be the same thing for every problem in this section, and that is that at least one of these proportions is wrong. Okay, then you define your proportions. Piece of R is the portion of all the flowers of this plant that are red. Piece of Y is for yellow, and piece of W is for white. Then we have our assumptions. Okay, just like the last problem, it says an SRS was taken, so random conditions met. There must be at least 1,240 of these plants for our sample size to be less than or equal to 0.1 times our population size, because we're doing sampling without replacement here. Okay, so we have to have a big population. So you just always multiply your sample size by 10. And then lastly, once again, we do not have normality in this with chi-squared. And so you just look at the expected counts, okay? And make sure and show the expected counts if they're not shown. So all the expected counts are at least 5. How did I get those expected counts? Well, once again, so what we did to get the expected counts, you just multiply your sample size times each proportion. So for the red, you would say 124 times 7 divided by 11, just like that. So the first that's the expected count for red. For yellow, it'd be 124 times 3 divided by 11. And then for white, it'd be 124 times 1 divided by 11. And that is that. And so there's your expected counts. So if the null were true, this is how many we're expecting to occur in the sample. If we did many samples like this, this is what we would expect at the average. Please do not round these values of expected counts, okay, to the nearest integer. Okay, so anyway, so there's my expected counts, right, like that. So how do we get our mechanics? And so you don't have to do everything that I did on that last problem. And so this is what we'll do, is we'll hit stat and edit, and in list 1, let me clear these out. We're going to put our observed counts. So in list 1, our observed counts, let's see, we have 70 for red, we have 47 for yellow, and we have 7 for white. My expected counts, and I like getting that somewhat exact number. And so what I'm going to do is I'm going to do what I just did, which is I'm going to say my expected count for red is 124 times 7 divided by 11, right, like that. Then for white, it's 124 times 3 divided by 11, right, like that. And then lastly, for white, it is 124 divided by 11. And so there's my expected counts. And so now to get my test statistic and p-value, I'm going to hit the stat button. I'm going to go to test, and I scroll all the way down to chi-square goodness of fit test right there. So I hit enter on that. So my observed are in list 1, my expected are in list 2, my degrees of freedom once again is 3. That's the number of categories minus 1, and we just have 3 categories here. So number of categories minus 1, so it's 2. I do calculate, and there's my test statistic p-value. There's my contributing parts. So my chi-square test statistic is 7.176. And if you would look at this, so the red contributed 1, a little more than 1. The yellow contributed 5. And then the white contributed like 1.6. So if I was doing follow-up analysis, I would say yellow, the difference in yellow contributed the most to the chi-squared. It had the biggest difference, the biggest relative difference. And so anyway, and so we write those numbers down there. Those are the only 3 numbers you have to write. And then we do our p-value statement, which we've been doing the same p-value statement. If the p-value is low, you reject the null and have convincing evidence for the alternative, which you say in context. That's exactly what I did here. This p-value is below 0.05, so I reject the null. there is convincing evidence that at least one of the proportions of flower colors in the null is wrong. And so there you go. That's chi-squared. If you have any questions about it, please send it to me and I'll be glad to chat with you. And I just hope you have a wonderful day.